All right, sweet. So what we're going to do is we're going to talk about the lungs, okay? And essentially how we carry oxygen from the air into our lungs, from our lungs into the blood, and so on and so forth, okay? So we're going to talk about first and foremost, of course, now it doesn't want to let me write on my screen. We're going to talk about, see if I click over here, if that will do it. Okay. We're going to talk about the mechanics of breathing, which we're going to call ventilation. We're going to talk about the mechanics of what we call pulmonary diffusion. And pulmonary diffusion is going to very, very simply be how we're going to move oxygen and CO2 at the lungs, and then how we carry O2 and CO2 in our blood. We're going to talk a little bit about how we use the pulmonary system and our ability to carry CO2 in the blood to help us balance acidity. And then with the very, very end, we're going to talk about changes with exercise and something called the gas exchange threshold. Okay. So, all right. So as we start off, most of this stuff I know is going to be review for you guys. Okay. The mechanic part at least. Okay. But the idea of what is called pulmonary ventilation. Pulmonary ventilation is in many ways the pulmonary analog, so the lung analog to cardiac output. Okay. What we're going to do is we're going to use ventilation. We're going to use the act of breathing to bring oxygen in and to remove CO2, get that oxygen into our blood, and then that way we can circulate it out to our different tissues. Okay. But it's really, really going to be this gas exchange portion that's going to be the really, really big, kind of piece of everything. Okay. The end part is going to be a little bit confusing. When we talk about how we regulate gas exchange and how we regulate acid-base balance, gas exchange is not too difficult, but the acid-base balance part is going to get to be a little bit trickier. Okay, so we'll work on that. We'll probably do a little bit more of that in class on Wednesday. Okay. I don't know what is happening. Okay. All right. So we've done those two things. So as I said, we're going to break this idea. We're going to break what happens in the lungs down into 4 components. So we're going to take each of them kind of in turn. So the first component is what we traditionally think of as breathing, and that is called pulmonary ventilation. Okay. So you may see this in the textbook or in other things that you interact with called minute ventilation, which is very often abbreviated as VE. Okay. V subscript E is going to have units that are liters of air per minute. Okay. And so pulmonary ventilation, this is the lung analog of cardiac output. It's going to have 2 components. One is called tidal volume, which is the analog to stroke volume, and then frequency, which is the analog to heart rate. Okay. So tidal volume is the amount of air that moves into or out of the lungs per breath. And then frequency is how many times we breathe in a minute. Okay. And so you multiply those 2 things together and we get a volume of air that moves. That's what we're going to call, or we're going to refer to as minute ventilation. Okay. Our second component is diffusion. So we've brought this air in and we're going to discuss how we move oxygen from the air into our blood and how we move CO2 out of venous blood into our lungs, into the air, so that we can breathe it back out. Okay. We'll then talk a little bit about gas transport. We'll talk a lot about hemoglobin, which I know we've already done, and we'll work our way through how we're going to use partial pressures to be able to move O2 and CO2, put that O2 onto hemoglobin, and then move it around to our tissues. Then there's going to be this idea, which is oftentimes referred to as internal respiration. I don't like the word respiration. I think the word respiration sometimes gets us in trouble. Okay. But that's how the textbooks tend to refer to it. Internal respiration. So respiration, for some context, has in the past meant metabolism. Okay. It's meant sort of an actual biochemical process What we're going to use it in our purposes is just going to be once we get sort of O2 and CO2 into our blood, or we get the O2 especially into our blood, and we get it out to the tissues that we want. How are we going to be able to then transfer it from the capillary blood into skeletal muscle, into the cardiac muscle, into the brain, etc. Okay. So that's how we're going to do those things. All right, I'm going to try from here to figure out, I don't know how it keeps doing this. I don't want it to do, it won't let me scroll from here. But when I go to this, then I actually can't see you guys, and that makes me very sort of anxious. All right. So in talking about pulmonary ventilation, we need to talk about the lungs a little bit. I know you guys have seen all of this. I only really want you to know these three structures, okay? The lungs, the alveoli, and the capillaries that are going to surround all of those alveoli. Okay, that's really going to be the only piece of this. We're not going to talk about what is happening in the nasal cavity very much. We're not going to talk about how we humidify the air. We're not going to talk about what's going on in the trachea or any of those things. We're really, really going to focus on the mechanics of how the lungs change their volume to allow air to move in. We'll talk a little bit about the bronchiolar tree down to the alveoli, and we'll spend most of our time talking about what is going on here at this capillary to alveoli interface, and the place where we're going to actually move O2 and CO2 from one place to the other, which is what this entire system is set up to help us promote. Okay. Okay. So mechanics of breathing, this is the fun part that I want everybody to do. Okay. Wherever you are, you guys, I want you all to take one big deep breath in and hold it. Okay. Ready? So now out. Okay. One more in and out. So we've now all done our deep breathing for the day. But the thing to keep in mind when we go through and talk about inspiration as you bring that air in, okay? As we bring the air in, what we are doing is we are going to expand our chest cavity, all right? You are going to drop the diaphragm. It's going to raise, right, the volume inside your chest cavity where your lungs are. That lowers the pressure. Okay, so when you stand up straight, it's easier to breathe because it helps to lower the pressure, right? Anytime you've ever done any sort of exercise and you're having a hard time catching your breath and they ask you to stand up and put your hands up on your head or something of that nature, they're trying to get you to be up and to open up that airway and to open up the chest cavity to lower pressure. All air is going to move in and out of the lungs via pressure gradients. So very, very small pressure gradients. That's all that we're going to need to have, okay? Now, you guys can do a fun thing during inspiration. What I want you to do is, has anybody ever had an asthma test? Anybody ever had to go and get tested for asthma or do some sort of pulmonary spirometry testing or anything else where they're trying to measure your inspiratory volume or your expiratory volume or anything else? We got anybody that's got asthma? I had to do this when I was in high school. They thought I had asthma. It turns out I just had bronchitis for like 8 straight weeks. Um, and I would go and we would go. It was during the spring, and so it was when I was playing baseball. I would start coughing when I would start to run and warm up at a baseball game, and I would cough until I puked, and then I would be fine, and then it would stop. It was a weird sort of thing, but they did all this testing. It's terrible because it's like you need to suck as much air in as you possibly can. So you go and you go it all the way. That's an active process. At rest right now, you guys are just going to sort of passively allow the diaphragm to move. The diaphragm's not passive, but everything else is, and air comes in and out. You'll never have to think about it, okay? Similarly, during expiration, when you exhale, the diaphragm relaxes, it pushes itself back up, squishes the internal volume, air goes out. But if I asked you guys to, you all can forcibly expire and try to blow all the air out of your lungs if you want. You can try to expire for 20 or 30 straight seconds. It's awful and terrible, right? But just think about you're going to go and you're going to keep forcibly exhaling. Okay. So to do this, we're going to use not only the diaphragm, but we have some accessory muscles that we have conscious control over. And so these are going to come into play during exercise to some extent, but not fully. Okay. All right. So here's just kind of a graphic depicting the things that we just went through. If we're going to be at rest, right, here's your diaphragm. When you're going to inspire, the diaphragm contracts, right, and it's going to drop. And as it drops, then this area up here where the lungs are gets bigger. That lowers the pressure. And so then air wants to move in from outside into your lungs. And then when you expire, you relax and the diaphragm goes back up here to its higher position, which squishes that volume down, shrinks that volume, which then raises the pressure inside. And then you open your mouth or your nose, and air pressure inside your lungs is higher than air pressure outside your body. So then air will want to move out. Okay. That's how this process is gonna proceed. Okay. So I told you guys we don't really have to know much of this. But I did want to point a couple of things out about the way, right, that the bronchiolar tree is going to be set up. And so if we look up here at the top, you can see the trachea. The trachea is then going to branch into sort of the primary bronchus, and then those are going to begin branching out, much like the arteriolar tree does. And it branches into these smaller and smaller and smaller pathways or tubes that are eventually going to branch all the way down and have these little small air sacs or the alveoli at the very, very end. Okay. So high up in the tree from your trachea through some of the primary bronchi is what we call the conducting zone. Okay, the conducting zone. And the big part of the conducting zone is this is just a place for air to move. It humidifies it, it filters it, right? Lots of mucus and things in these areas. It's going to help us out, but no gas exchange occurs. So you're not doing gas exchange up here in your trachea or even into the primary bronchi. Where all the gas exchange takes place is after it branches out way, way, way down and we get nearer and nearer to the alveoli. And that's called the respiratory zone. Can Dory come in here? Yes, Dory can come in for the moment. Is she causing y'all problems?
Yeah, my mom got real bad.
Okay. Okay. Here we go. Hi, Dory. So Dory has made an appearance. I don't know if you guys can see. My pup has come. Dory's in trouble. She spilled a drink downstairs, apparently. Here, Dory, hop up. Come on. Hop up here. So the one crazy basset is here. Dory, you want to say hi? Okay. All right. So this will be interesting because she's crazy. And I'm in our bonus room where Ellis has lots of toys. So you will hear lots of Dory no over the next few moments with everything. So we were talking about the respiratory zone and what all goes on there. The big thing to take away, right, is that where we meet in the respiratory zone, where the alveoli meets the capillaries, we are going to have an area that is essentially two cell layers thick. There's the outside layer of the alveoli. There's the layer or the membrane on the capillaries that are there, and that creates this very, very small area to get through where we can have gas exchange, which is going to help us out in those areas. Okay. I don't know what's happening or why I got to get to the slideshow, but there we go. Okay. So the book talks about this, and I want to mention it. But again, I'm really not going to ask you guys too many questions about any of this stuff. But when we look at pulmonary ventilation, it normally happens in two particular places. So you have what is called dead space ventilation, and then you have alveolar ventilation. And what I want you all to take away from this is very, very simply that there is going to be air that we move into and out of the lungs every time we breathe, and not all of it is going to make it down into the alveoli from outside air, nor is all of the air that gets into the alveoli, stuff that gets into the alveoli, going to make it all the way out every time with every breath. Okay. And so that is this idea of dead space ventilation. Part of each breath remains in the conducting zone, doesn't reach the alveoli. Okay. We call that anatomical dead space. That's the sort of upper portion, especially of the pulmonary tract. Okay. And then what actually reaches into the alveoli is really going to be the volume of air that's going to have a real meaningful sort of output and ability for us. Okay. All right. Dory, no, stop that. Stop that. So I mentioned this idea of the place where we're going to have the wall of the pulmonary capillaries and the wall of the alveoli. That's going to be this 2-cell layer kind of thick thing. Dory, come here. Dory, come here. Come here. Come here. Hop up. Come on. Okay. This is called the respiratory membrane. This site, this area is the respiratory membrane. And so that membrane is going to be where all of the gas exchange action is going to take place, where all the O2 and CO2 movement is going to be, where we're going to have those red blood cells be in very, very close contact with the alveoli. Okay. So here's an electron micrograph of what all of this looks like. Okay. And so in the part of the picture on the left, you can see this is a pulmonary capillary. This is the alveoli. And then this area right here where they're going to come together, this is the respiratory membrane. And so you're going to have red blood cells in here that are going to capture oxygen moving from the alveoli in, and they're going to give up their CO2 and move them out. On the picture on the right, you can see multiple capillaries that are existing, wrapping themselves around an individual or several alveoli. And then the things that you see in them, those are individual red blood cells. And so you have these very, very small air sacs with this high network of capillaries in and around them that's going to let us get really, really close from a blood and a red blood cell perspective. Okay. So at the at the respiratory membrane, we are going to experience pulmonary diffusion. Okay. And so the real thing to take away here, very, very simply, is that this is the place where we're going to bring oxygen from the air and replenish our O2 supplies into our blood. So essentially, venous blood makes it to the lungs. It has a low O2 content, which is really important that it's low. There's higher O2 content in the air in the lungs, and it's going to move in. Okay. And then we're going to have in that venous blood, we're going to have higher levels of carbon dioxide. And that carbon dioxide is going to be in a higher level than what is in the air. And so it will then move from the venous blood into the air in the alveoli, and then it will go out and get breathed out. And that's why you breathe out. The air you breathe out has more CO2 in it than atmospheric air. Okay. So all of this works for a very, very simple reason. Okay. O2 moves, CO2 moves, any of the gases in that are going to be contained in the air are going to move because of something called a partial pressure gradient. Okay. And so this is a little bit of a tricky concept, but hopefully it's something that you guys have all had before, and then it will make sense. Okay. The idea behind partial pressure laws is that atmospheric air, let's just say we are at sea level, which we're not too far from here in Oklahoma. Atmospheric air exerts a certain pressure on everything that comes into contact with it. At sea level, atmospheric air has a total air pressure of about 760 millimeters of mercury. That 760 millimeters of mercury can be broken down in relation to the composition of the gases in our air. And this is going to get us this idea of the partial pressure laws. And what we see basically is that atmospheric air is 79% nitrogen. It's almost 21% O2. And then there's a tiny, tiny, tiny fraction of atmospheric air that is carbon dioxide. And so when we calculate partial pressures, what we're going to do is you take air pressure, so you take 760, and you multiply that 760 by the percentage of the air that is made up of a particular gas. So in this example, we would use nitrogen, that is 79.04% of our air. You multiply that, so you take 79.04% of 760, and you get a number that is about 600 or about 601 millimeters of mercury. So the partial pressure of nitrogen in atmospheric air is about 600 millimeters of mercury. Okay. Similarly, you do the same thing for oxygen. You arrive at a number that in atmospheric air, the partial pressure of oxygen is about 159 millimeters of mercury, and the partial pressure of carbon dioxide is very, very, very low. It's about 0.2 millimeters of mercury. The reason that these numbers become so important is that if there's this partial pressure of oxygen in the air, so it's at 159, any place that that air comes into contact where there is less than 159 millimeters of mercury of oxygen partial pressure, oxygen will want to move from that air to the new location. And so this is how we're going to move stuff into and out of our blood, okay? From the air into the blood, and then for carbon dioxide from the blood into the air. So let's look at our numbers. And you guys don't have to know these numbers, but we are going to use these. These are the real kind of mostly functional numbers that we have at sea level. You don't have to memorize them, but I'm going to use it to try to illustrate sort of how we generate these pressure gradients and how and why that becomes so important. Okay. If we look at O2, the percentage in sort of atmospheric air is almost 21%. Our percentage of CO2 is very, very low. Okay. Dory, what are you doing? Dory is sitting next to me and she's biting her paws and whimpering, and now she's trying to bite me. So super fun times. Dogs are the best. We look in dry air. When the air makes it to the alveolar air, you're going to note that we have a lower oxygen partial pressure and actually a higher CO2 partial pressure. And most of this is going to have to do with the fact that we are humidifying the air. And so as we dissolve oxygen into water, it's going to change the partial pressure a little bit. So what we're going to see is that O2 partial pressure in alveolar air is about 105. The O2 at rest in venous blood is about 40. So there's going to be a gradient of about 60 millimeters of oxygen partial pressure. Okay. So there's going to be this large, large gradient. During exercise, we're going to take more O2 out. So the partial pressure in venous blood is going to fall. So that gradient will get bigger. Now, when we look at CO2, you have a much, much smaller gradient. That in arterial blood, CO2 is about 40. In venous blood, it's about 46. So you have this really, really, really small pressure gradient. Okay. Dory, stop that. Stop that. This very, very small pressure gradient. Despite the pressure gradient being like 10 times less, it's actually much, much easier to move CO2. You can move more CO2 per the pressure gradient, which is some chemistry and things that we're not going to get into in class, okay? So again, this is just sort of showing at the lungs, and then this is showing the arterial side over here. This is showing where like we'll use a muscle as an example as our body tissue, and then this is the venous side over on this instance, okay, here on the left. And it's just going to show the relative partial pressures, right, in alveolar air, and then what's going to happen in arterial blood, what's going to happen when we get to the cells, and then what's going to happen and what it's going to look like in venous blood when the whole system is going to move itself back around. don't have to know these numbers, but this is a nice visual representation of it's higher O2 in the air, right? 40 versus 100. It diffuses until those are essentially equal, right? We're going to have 46 CO2 in venous blood. Then it's going to give it up until it's about 40 and matches what's in the air. And that matches then what's in arterial blood. And so then that's going to let us move this around and around in this particular way. Okay, so how do we carry oxygen and CO2 in the blood? Oxygen is pretty easy. Okay, oxygen is pretty easy. The vast majority of oxygen is going to be carried in and on in the blood on hemoglobin. Okay, so it's like 98% bound to hemoglobin. This allows us to transport 50, 60, maybe 70 times more oxygen in our blood than we could if it was dissolved in plasma alone. Okay. So we do have a little bit of oxygen that will just be dissolved in our blood plasma. It's about 2% or thereabouts at rest. So there's a little bit that's there, but because we have hemoglobin, we can bind way, way, way more. And so that's why hemoglobin in blood is so important for sort of life in general. The other good thing about hemoglobin is, especially as we are relatively at sea level and you have good pulmonary function, hemoglobin or O2 saturation is usually, okay, usually going to be somewhere between 95 and 100%. So if any of you guys, go back out of this, if any of you guys have ever had the little things where you do your pulse oxygen, I should have run downstairs and gotten ours today, but you go to the doctor, they put a little thing on your finger and it tells you what your pulse oxygen is, right? That is measuring hemoglobin saturation. It shines near infrared light into your muscle or into your tissues, and it bounces back and it gets absorbed um, by the stuff in and on the hemoglobin, and it can tell us those kinds of things. The good part about this, we have lots of O2 in the blood, we have lots of hemoglobin, and it all tends to be bound, okay, is it allows us to have much, much more carrying capacity for oxygen in our blood than is actually required at the tissue. Okay. So we have a very, very large reserve for the most part, as long as you have proper hemoglobin concentrations in the blood and proper pulmonary function. The big issue and where things get into trouble, and this was really noted during the COVID pandemic, and I guess we're still in a pandemic. I don't know at what point COVID has just become ubiquitous everywhere, was that it would actually cause impaired pulmonary function. And because of the impaired pulmonary function, then we were unable to bring in enough oxygen and properly saturate hemoglobin. And that's where we get into trouble. So lots of hemoglobin saturation problems you rarely have to do with hemoglobin. Sorry, Dory's trying to climb around onto the other side here. Dory, what are you doing, sis? Oh my gosh. Dog. Okay. So let me see what happens here if I can manage this. Do you want to just sit in my lap? Usually I don't let you, but she's the neediest dog that you've ever seen. Hi. Are you better now? I'm trying to teach class, you crazy lady. No, no kisses. No kisses, dog. No kisses, okay? Glad this is being taped and captured for posterity. No. Oh my gosh, you're so gross. Okay. Okay. All right. We're going to try to keep talking and we'll see how the dog does. Okay. Okay. So this is going to show a little bit about the hemoglobin structure and how all of that generally works, right? what you can see from this is that at the center of hemoglobin, we have iron. And so it's this iron that is very, very, very going to be very positively charged, which makes it very highly attracted to oxygen. And so, as a part of all of that, this is why getting iron in your diet or taking iron supplements, if you're having a little bit of issues with your red blood cells, is so, so, so important. Okay. Okay, so you guys have probably seen this curve before. And again, I'm not going to make you guys draw this, but I do want you to be able to appreciate some of what happens during exercise with all of this. So what we've graphed here is something called the oxygen hemoglobin dissociation curve, or the oxyhemoglobin dissociation curve. And what you see on the y-axis of all of this is the percent saturation of hemoglobin. And then on the x-axis, you can see what is called this P little a02. This is going to be arterial, right? So arterial, no, I'm sorry, this is alveolar hemoglobin. Oh, I can't talk right today. Alveolar O2 partial pressure. Goodness gracious. Okay. Sorry, my wife came and rescued me from Dory, and so Dory was left, and so there was lots of sort of things going on over here that had distracted me. So what I want you guys to note from all of this, okay, is we look at the way the curve is. It's this kind of curvilinear thing where there's this very, very steep increase as alveolar O2 pressure rises. And then it's going to level off up here when we get to this very, very sort of near kind of what our actual normal alveolar PaO2 is going to be. All right. And so up here, we're very, very close to 100%. And what happens basically is as this begins to sort of work our way backwards, then you're going to lose oxygen off of the hemoglobin. Okay. And so what we get basically in this area here where it's very, very steep is going to have some role in our ability as we're going to put ourselves on this side as we get near our tissues. Okay. So a cool thing that happens is something called the Bohr effect. And what happens is when we exercise and pH begins to fall in muscles and in the blood, and due to increased muscle temperature, this entire curve begins to shift to the right. And as it shifts to the right, it makes it easier for us to actually unload, okay, unload oxygen off of hemoglobin into our tissues. And so we're still doing fine, even though it shifted to the right. We're still doing fine at the level of the alveoli. Okay, we can still get very, very near to 100% saturation, but because it shifts sort of down and to the right, it makes it easier for it to unload. So exercise actually helps us to get and remove CO2 and O2 from the blood. Okay. Okay, so in one that's a little more interesting and is going to play a really, really big role in helping us balance acid-base balances in the blood, that's going to be how we transport carbon dioxide in the blood. Okay, so there are three primary ways that we transport CO2. The first is going to be dissolved in the blood. So we dissolve more CO2 in our blood than we do O2. Remember, O2 is about 2%. We're going to dissolve into the plasma somewhere between maybe 7, 8, or about 10%, okay, CO2 in the blood. We actually bind some carbon dioxide onto hemoglobin, and that's somewhere between about a fifth to a third, so 20 to 30%, excuse me. And we call this carb amino hemoglobin. So the O2 leaves at the tissue level, and then CO2 comes in and binds up back onto that hemoglobin, displaces some of that oxygen or takes its place, and we're going to carry some that way. And then the vast majority, though, somewhere between about 60 to 70% of CO2 carried in our blood is carried as bicarbonate. Okay. And bicarbonate, we're going to end up with bicarbonate through a chemical process where when you bring CO2 into the blood, okay, it is then going to be dissolved, as we'd said up here. It dissolves into the plasma, which is mostly water. When you put CO2 and water together, you get carbonic acid, okay? You then have carbonic acid that is now in water in your blood. So you put an acid in water and it dissociates. So you get a free hydrogen ion and a molecule of HCO minus, which is what we call bicarbonate. And so you have lots and lots of this HCO minus floating around in your blood. You've got some CO2 that stays as CO2 in the plasma, and you've got some that's going to be bound there. Okay. Now, it's this bicarbonate that we see down here that's going to be so important for helping us to balance pH, okay, in the blood, because that bicarbonate is a base. Because it has a negative charge on it, it will want to go around and it will want to bind free hydrogen ions at various points and sort of run this reaction in reverse and lead to making water and releasing extra CO2 for us to be able to breathe out in our lungs. And we'll talk our way through a little bit more of this as we progress. It may not be today. We may get to that on Wednesday in class. Okay. All right. So let's talk about what happens with breathing when we exercise. And it's all just exactly what you think. Okay. Breathing frequency goes up and breathing depth goes up. So pulmonary ventilation or minute ventilation increases in relative direct proportion to exercise. Okay. You breathe more often and you breathe more deeply. You breathe deeper, I guess, every time that you're going to go. We have to have these changes, okay? Because it allows us to bring in more oxygen to supply that need at our tissues. It helps us remove the extra CO2 that is being made at the tissues, and it helps us to maintain the proper pH in both the muscle and in the blood, okay? And so more breathing means that we're removing more CO2, so we're putting more CO2 into the blood in all of those ways. There's going to be more bicarbonate. There's more bicarbonate. It helps us to buffer any of that acidity that's being made by making lactic acid. Okay. So that's why we have to have these changes. If these things don't work correctly, exercise cannot continue, exercise cannot progress. And it's not just about bringing in oxygen. It's also about what we're doing to regulate CO2 levels. Okay. Ventilation is controlled by the brain. And much of this stuff in the brain, it's all going to come back into these, what we call respiratory centers, which are located in the medulla. Okay. The medulla or these respiratory centers are going to have input coming in from what we call peripheral chemoreceptors that are going to be in the carotid arteries and in the aortic arch. Peripheral chemoreceptors are monitoring oxygen levels and CO2 levels in arterial blood. We have stretch receptors that are going to send information, these stretch receptors in the lungs. So as you begin to breathe more deeply and you stretch your lungs out, those stretch receptors are then going to send input to the brain and say, hey, we're breathing deeply. Let's go faster. You have input that comes from proprioceptors. So things that are going to come from muscle spindles and the Golgi tendons and things in the muscles and the joints. There's going to be input that comes from changes in temperature. We also have central or brain chemoreceptors, okay, that are going to monitor oxygen and CO2 levels in the brain. And then finally, you have input from the motor cortex. If I ask all of you to consciously think about breathing faster or breathing more deeply or not doing those things, you have some level of conscious control from up here in the motor cortex that signals back down into those centers. Now, I want all of this to be really, really careful with everything and say that you can exert conscious control, okay? But that conscious control will only last for a little while. If I ask all of you to hold your breath, you can only hold your breath for so long, right? At some point, the input from all of these other things is going to be that way. Ellis, would you like to say hi to everybody? No? Are you sure? Okay. Ellis is now here. You sure you don't want to wave at everybody and say hi? No? Okay. So she was here. She was peeking around the edge of the screen for you guys. You can hold your breath for a while, right? But at some point, you're going to have to breathe. You cannot use this conscious control to overcome this for a particularly long period of time, more than in really, really well accustomed people, maybe 3 or 4 minutes. Um, and so it's much easier for us to tell it to speed up and do things like that. Okay. Okay. So again, this is just that same kind of stuff, but it's showing the areas where there's going to be feedback, right? Here is showing a central chemoreceptor. So chemoreceptors, looking at medullary. So in the medulla, looking at interstitial fluid, looking at hydrogen ion levels. It also is going to help us to monitor O2 and CO2 levels, right? We have upper airway muscles. We're gonna be looking at sort of what are we doing? Can we actually have conscious control there? Feedback in the carotid chemoreceptors, measuring arterial O2 and CO2 levels, measuring hydrogen. Okay. And then we've got these afferent and efferent feedback things that are going on. Okay. Okay. Can you guys hear Ellis? Yeah, can y'all hear her? We are playing with our pirate ship over in the corner. And other stuff. Okay. So let me go through like 2 more things here, guys, and then we'll go ahead. I know we're about out of time and we'll turn you guys loose. Okay. So what I want to emphasize about the things that control breathing. Primary thing that controls breathing is CO2 levels. Okay. Is CO2 levels. We are going to sense especially carbon dioxide levels in your carotid arteries and in the aortic arch. So it's these chemoreceptors. Increases in CO2 immediately drive an increase in breathing. Okay. This is why when you hold your breath, it raises blood CO2 levels. Okay. As we raise blood CO2 levels, that immediately stimulates the respiratory centers to make us breathe more deeply. Okay. This is going to be the primary thing, and the reason that metabolism is so closely linked to increases and changes in breathing. It's as we increase aerobic metabolism, CO2 levels are going to rise. We're not super perfectly efficient at releasing all the CO2 at the lungs. So arterial levels increase, and then that lets us drive this increase in breathing. Okay. Okay. So I think for now we'll stop here for today. We'll finish the rest of the stuff up on Wednesday. We'll spend the rest of our time then on Wednesday. We can do a little bit of review for the test. Um, and then we'll have our test on Friday. Okay. Anybody have any questions or anything that I can help you guys out with now before we go? Speak now or forever hold your peace. Can I interest anyone in a crazy basset hound? Would anybody like to dog sit for a couple of weeks, or arrange a play date with Dory with your dog to run them down? That would be super on all of that. Ah, look who's here. You see them waving at you, Ellis? You want to say hi? Okay. All right, guys. Yep. At the end now, we'll see you guys Wednesday. Everybody be careful today. If there are in fact more tornadoes, please take shelter, etc. Okay. All right. Bye, everybody.